So welcome to this final and 10th session of the course on Bayesian modeling, inference prediction, and decision making. You guys are the heroes here, the real core. There's about 25 of us left from an initial lot of more like 50. And so you are to be congratulated for your stamina. I have some new things on the webpage, and then we'll get right to some ideas. First is a plug. There's a set of ideas that are good to know about under the heading of approximate Bayesian calculations with large data sets, integrated nested Laplace approximations, INLA for short. And we have been lucky enough to have attracted the world expert on this topic to come to Santa Cruz in a few weeks and give us a short course on this. Oh, sorry, got all that noise. His name is, I'm going to try to pronounce it right, Håvard, I think is his first name, and it's something I really, he's from Norway. And on Monday, the 15th of April, tax day, better things to do on tax day than pay taxes, perhaps, we're going to have a nearly day-long short course. It'll run from 8 o'clock in the morning to 3:30 in the afternoon. He's made really high-quality R code available to implement the idea for this approach to approximate Bayes calculations in large data sets. And the class of models that the INLA software can fit is quite impressive. The general class of such models is called latent Gaussian Markov random field models. And there are many things that you're perhaps familiar with that are special cases of this model. Namely, all sorts of time series models, which we haven't had time to talk about in this class, generalized additive models, which I could say a word about sometime today, generalized additive mixed models for longitudinal data, geo-additive models, regression-style models with non-parametric fitting of interaction terms between the continuous predictors, and stochastic volatility models that get used a lot in finance. And Håvard has created a very high-quality website that gives all sorts of information about the latest developments about INLA. A bit further down in today's webpage on 22 March, I've put a link to a document he wrote, a short document only 3 pages long, in which he describes the class of models and gives examples of how you can fit, as I mentioned, all those different classes of models I mentioned before are all special cases of the model he's interested in. So I very much recommend it to your potential attention. It would be another more or less day invested in your life in trying to learn more about how to do Bayesian calculations in complex modeling settings. But this course would serve as an ideal preparation for you, and I hope that I don't know, 5 or 10 of you might, in fact, be interested in coming. We are able to take all comers. The room I've set it up in holds far more people than we'll be able to attract, probably. I'll be talking with the San Francisco chapter of the ASA and the Bay Area chapter of the ACM to put links onto their web pages just in the next several days, because this has all just come together quite quickly. The registration fee is only $50 for really high-quality material, and that basically covers essentially 2 beverage breaks and lunch and various sorts of room rentals and setups and so on. So I'd like to ask if you could please send an email to me indicating if you plan to attend, if you do, and then I'll return by email. I'll send you instructions on parking and exactly where on campus the thing will be taking place. The idea would be then to show up a little bit before 8 a.m. That morning in the courtyard between our 2 engineering buildings on the UCSA campus, and you just bring a $50 check made out to University of California Regents, and we'll register you quickly, and the course will start at 8:15 that morning and run with 15-minute breaks and an hour and a half for lunch from 8:15 to 3:30. He should be able to cover quite a lot of ground during that time and show you quite a few demos of his code. I'll need to know from you if you're coming, please no later than Thursday afternoon, the 11th of April. at 5 o'clock that day so that I could collate all that stuff by the Friday morning and get in touch one last time with the catering people to make sure we have the right number of lunches and so on. Okay, so what else is new on the web page? I have made the mapping of topics. I've finished it now because here we are in week 10, so it's no longer an approximate mapping of topics. It's the right mapping of topics. And we have some new material on the 22 March. There's some extra notes from last week that have been posted since last time. There's an interesting guy in England named David Mackay, and he looks at statistics from an information theory and machine learning point of view, and he has a quite excellent book-length manuscript that you can buy from Cambridge University Press, but he made the PDF available for free to anyone who is prepared just to do on-screen viewing. I gather either he has set things up so that you actually can't print from this file, or he's just asking people not to print it. And then if you want a hard copy, you can get it for 30 British pounds or $50 by going through Cambridge University Press. All sorts of interesting ideas in there. So if you want to keep doing some reading, and in this case, from a information theoretic and machine learning point of view, that nicely supplements a bunch of the stuff we've done in here, that would be a good place to read. And I've shown you Hovard's little document that helps you understand what's going on in INLA. And I mentioned last time, but here's again, I was invited to write an encyclopedia article on all of Bayesian statistics in about 15 pages for something called the Encyclopedia of Complexity and System Sciences, I think is what it's called. And you'll find much of what we did this 10 weeks all wrapped up in one 15-page document. So that could be a place that you could go to review everything we've done and solidify your understanding of the terms. And then we have the videos for all weeks 1 through 9 are available, except that unfortunately some of them were corrupted when they tried to recover where they were. So for example, last week apparently is fully there, but the previous week, parts 2 and 4 were corrupted, and the Google people are working on trying to fix that. I'll do my best to get the good versions of them posted in the course of time, and of course we'll have the videos posted about a week from now for the session today. There's some new code down here. I'm going to show you how to answer the question, could the data have arisen from a particular model, and do answer that question in a well-calibrated fashion, and have some R code that shows how to do that. And I have brought you a large data example, a randomized controlled experiment with about 12 million observations in each of the treatment and control groups, and we'll probably conclude this afternoon by looking through that. Also, we're going to define the deviance information criterion, DIC, today, and give an example in which it misbehaves quite badly. And so I have some WinBugs code for that. And I believe that everything else in here is stuff we've seen before. So I'd like to begin by catching up on some of the remaining material in, we're still working on Bayesian model specification, which is a topic that's so broad and deep that we've spent a number of weeks on it, and we're now up to about page 50-something in this document. I'd like to finish that this morning and show you some more material. There's now a section 1 and a section 2 of the Bayesian model specification. And we're going to talk about log scores more than we have done before. And today I want to give you some details about how to actually implement log scores. I have some code that shows you how to do that, and I need to explain how the code, the math on which the code is based. So let's forward through to roughly page 50 or so. We were talking, when we worked with this material before, about various methods for answering what look like quite fundamental questions. I'm on page 44, the bottom page 44 in part 5, section 1 of the organized notes. I've given you a modeling algorithm on this page, which can help guide a search through model space, and we can do this in a way that doesn't involve overfitting, using the method that I have mentioned, described as calibration cross-validation, in which we partition our data into three non-overlapping and exhaustive subsets called modeling, validation, and calibration. And now we fiddle around in M, doing all sorts of assessments of many different models, and then you can go and see how well those models validate in V, and you'll discover they often don't. So then this method allows you to go back and remodel in step B and revalidate in step C, and so fiddle around quite a lot. And then at the end you have some data set aside that serves two purposes. It makes your inferences from the data in parts B and C. Your uncertainty bands are a little wider, appropriately so, in order to account for the uncertainty in the modeling process that you developed in an iterative fashion. And also we have data left over to see how well the entire iterative process calibrates on new data. So I recommend this as a general all-purpose way of coping with model uncertainty in a fashion that will remind you of how you already do data analysis, but not requiring you to learn new methods like Bayesian nonparametrics, not requiring you to learn new methods like Bayesian model averaging, although I've shown you information about both of them. This is a kind of overarching approach that you don't have to bring in any heavy artillery such as Bayesian nonparametrics to fully assess and propagate uncertainty in the modeling process. CCV, therefore, provides us a way, as it says on page 44, to pay the right price for hunting around in the data. And so now we can turn this modeling algorithm loose on the data, implemented typically by humans, because there are questions in it that are too hard to answer for robots at present, for computers. And some of those questions include things like the ones at the bottom of page 44. Is one model better than another? That's a question 1 type question. And question 2 type question, is a particular model good enough to allow you to stop looking for better ones? Because you have to have a rule for deciding whether it's necessary to go out and look for a new model that's better than the current one. That's Q1. And you have to have a rule for deciding when to stop. And I mentioned last time that even though those questions sound quite fundamental, they're not really, because in fact, underneath them are even more fundamental questions. Is Model 1 better than Model 2 for what purpose? And is Model 1 good enough to stop for what purpose? And as soon as you put down that purpose, you see we get to this principle that last time I called the modeling as decision principle, which says basically that making clear the purpose to which the modeling will be put, it looked previously like some sort of inference or prediction problem. It may have looked that way, but now model specification, when you think about the purpose to which the modeling will be put, is transformed into a decision problem, and we ought to be doing our best job to create utility functions that are specific to the actual task. I showed you last time that that was quite hard work through that case study with my former student, Dimitris Bouskakis, and I mentioned that people have a powerful desire to look around for generic methods that have a utility basis that can be used instead of specific problem-specific methods, which are hard to implement. And two of those approaches are Bayes factors and log scores. And last time I showed you the basic story behind Bayes factors, and I showed you what the basic problem was with them, and I recommended that you overcome those problems. We look at the Laplace approximation at the bottom of page 53. The basic difficulty is that you often find yourself needing to put diffuse prior distributions on the parameters inside each model, and it turns out by the way of having to calculate Bayes factors that the value of the Bayes factor can be unbelievably sensitive to small details in how you specify those diffuse priors on the parameters, and embarrassingly so. And so I recommended instead that you use a special case of Bayes factors called BIC, which is a version of Bayes factors that involves an implicit choice of a prior on those parameters, something called a unit information prior on page 55 in equation 22. And that's a nice prior to be using because it represents little information coming in through the prior, and what information is coming in is worth one vote and is centered at what the data has to say, so it basically can't be a wild vote even if it's only one vote. And so BIC, equation 20 on page 54, does seem to me to be a good way to go in making model comparison from a Bayesian perspective, and it has quite a natural form to it also. You see basically the first term in equation 20, it asks you to calculate minus twice the maximum log likelihood value under model J, because you evaluate the log likelihood function, and then you do so at the MLEs. The gamma j hats are the MLEs, or the parameter vector gamma j in model J. So minus twice the maximum log likelihood value. That's a number that quantifies how well model J fits the data. And then kj log n, tugging in the other direction, is a penalty term for having used too many parameters to achieve that particular level of quality of fit. And so there's an explicit trade-off there between goodness of fit on the one hand and parsimony on the other hand. And we all understand the need for that kj log n term. If we just had the minus 2 log maximum log likelihood value, then we would be encouraged to find more and more complicated models for the data that wouldn't validate well on new data. And so the kj log n term is to keep us from overfitting the data. So that's a good way to go. And another good way to go is log scores. And so basically I began to tell you about that several times ago, and I want to finish that today. What you do, it turns out, is you, in log score, on page 57 now, one natural way to think of implementing the idea is to evaluate the logarithm of the height of the predictive distribution at the data value that it actually obtains. And in order to avoid using the data twice, perhaps that should be the predictive distribution based on all the rest of the data except with observation I set aside. So that's what that y sub minus I notation means, as we've talked about before. That's what I'm going to call the cross-validation version of log scoring. And you calculate all those log heights of the predictive density. And so, okay. 1 second, please. I'm still my student Milovan Kirnaic and I discovered a few years ago something a little surprising. The cross-validation version looks like it would be hard to compute because you'd have to compute a whole bunch of different predictive distributions, one for each omitted data point. So we thought, well, let's try doing this where we just have one big predictive distribution in which we use the whole data set to predict each observation. That sounds a little circular because you're using observation yi both on the left-hand side and the right-hand side of the conditioning bar. But in fact, with n observations, when n is even moderately large, that's hardly going to involve using the data twice at all, and the effect disappears quite quickly as n grows. So we call that the full sample log score. Where did it go? The top of page 58, equation 25. Now we only have to compute a single predictive distribution, and then we evaluate the logarithm of the height of that predictive distribution at the actual data points and average. And this one, unlike BIC is set up because that minus 2 is multiplied times the expression in equation 19 back on page 54. Models that have small BIC values are better than big ones, models with big ones, and it's the other way around with log scores. We want to try to find a model with a big log score. So now we have two different ways to think about constructing model comparison methods. And that means I need to tell you a bit about how they compare with each other. But first I want to give you a few details on how to actually compute these log score guys. So in some notes that'll be posted by Sunday when I get back, I've written out some careful details. And I hope that that's visible in the room, at least partially. Would it be important? Perhaps I should scan in a little bit more and then move it around. Would that be better? For some reason, things are darker than they should be today. I guess perhaps I'll try making it bigger, and then I'll just move the paper around. Is that any better? Can you see it a little better now? The lamp does seem to be on, and yet things do seem to be darker than usual. Yeah, we can fiddle with it during the break. And so what I'll do here is try to move the paper around so that we can keep track of everything. I hope that, is the writing big enough in the back of the room so you guys can see it now? So this is the definition we just had, that the full sample log score is the average of the logarithms of these heights of the predictive. And the setup is we have a data vector, y1 through yn, and it's a simple problem right now with no covariates, and so that's like the NB10 example we worked with before. And we have a variety of different parametric models that we're comparing on the same data set. So model J has the following form. Model J is allowed to have its own parameter vector, theta j. Earlier, I guess I was using the notation gamma j on the PDF file, but it's the same idea. So model J has parameter vector theta j, and so if you knew what theta j was and that model J was right, the yi's would have a particular sampling distribution that is specific to model J, and then you put the prior distribution on the parameters of that model. So it's a standard Bayesian story as I runs from 1 to n. Now, we're supposed to be calculating that predictive distribution there. So to remind you of how that works in the Bayesian story, what we do is we predictive distribution, we take a weighted average in which we bring in the parameters, and this becomes the predictive distribution based upon the data and the parameters weighted by the Pasteur distribution for those parameters. So that's one of our basic integrals that helps to compute the predictive distribution. That there of course, is the Pasteur distribution in model J. And our usual trick, you recall how this goes. If I'm trying to predict the next observation, and I offer you both all the last observations and the truth about what the parameter vector is, you would say, oh, thank you very much, but I don't need the data, because if I know the truth, the data are irrelevant. So this expression here simplifies to the one that's called equation star. Namely, this is now the sampling distribution for the next observation, and we're taking a weighted average of those sampling distributions weighted by the Pasteur. So you'll notice that whenever you have some function times a density, and you're integrating over that or averaging over that, it's equivalent to computing the expected value of the function, because you remember how expected values work. They always take the form weighted average of the thing you're interested in weighted by the probabilities. That's the same as the expected value of that particular function there. So like it says at the bottom of the next page, another expression for the predictive that we're interested in, equivalent to what we had before, is that the predictive can be expressed as the expectation of the sampling distribution over the Pasteur distribution for the parameters. And that provides a natural Monte Carlo way to think about approximating that, because whenever you try to approximate an expectation, remember this is an expectation over theta j, then a simple Monte Carlo way to approximate an expectation is to take a whole bunch of draws from the Pasteur distribution for theta j and then just average that expression over those draws. So for a Monte Carlo approximation to the integral that we're interested in looks like this. We take an average over little m draws from the Pasteur, and we simply evaluate each row of the MCMC data set will provide a vector of parameter estimates, and now you evaluate this expression for each of those and average. That's a real standard Monte Carlo trick. And where did those draws come from? Well, you're doing MCMC. So you use MCMC to make little m identically distributed draws. I'll call them theta j star sub k. And that's a vector theta j, as k runs from 1 to m from the Pasteur, and plug them into this expression. And so finally, then, the full sample log score has the following expression to do it correctly. I'll call it triple star, this expression here, and the one up here that involves the Monte Carlo approximation I'll call double star. And so triple star says, well, you average over the data, the logarithm, the thing you get by Monte Carlo draws. And this is implemented with the NB10 example in a file that I've created on the web page called R code for the log score calculations. So let's take a moment and look at that code now. So I'll come back to the course web page and go down to the bottom and pull out the R code for the log score calculations. Where did it go? I've got the calibration code. That's funny. You see it there? not the one called calibrate the log scores. That's something else. I'm looking for the code called, oh, I know where it is. It's down here. Ah, good. In the NB10 case study, I have an item called R code for the log score calculations. So let's go ahead and grab that. And I'll grab all this and put it into a file. I guess I can probably right-click and save as, and put that in the desktop. And see if it opens okay. And of course it doesn't. It does that thing where it doesn't put in the line breaks. Thank you very much. So instead, I'll just go ahead and grab it and put it into a text file. There isn't that much of it anyway. And that way at least the line breaks are respected. Okay, so I have given you on the web page a bunch of files. So remind you how this worked. We had a Gaussian model for the NB10 data. The NB10 data, you recall, was that those 100 observations that represented IID weighings of that little block of metal. And we saw that the actual empirical distribution had much heavier tails than the normal. It looked like it had outliers in both tails. So your first model might have been, before you noticed the outliers, might have been a simple Gaussian model, like the one here called Model 1. And there's the data values again. And you would have to have the initial, the markup chain start somewhere, so those are the initial values for that one. Then we realized that a model in which we had a sampling distribution that had heavier tails was a much better idea. So we used a t-distribution with unknown degrees of freedom as the sampling distribution and tried to learn all three parameters: the location parameter mu, and the scale parameter sigma, and the shape parameter nu for how heavy the tail is. So that's Model 2. And that requires its own set of initial values, but it can use the same data set. So what I did was I ran Model 1, and then I was able to store the Markov chain Monte Carlo output. And I think let me show you how to do that so that you know how to do it once and for all. Let's go ahead and grab a WinBug session. And I'll bring the first model in and hit it with a new and put the model in there. And that's my model. And then I'll get another new, and this time I'll get the data file. And of course, exactly the same stuff I'm showing you now is easy to do in RJAGs. If you prefer that environment, you know how to translate between them. And one last new to get the initial values in there. Again, from the web page. Stop it. We'll start the chain off at reasonable values, and there we go. So I'll check that the model's okay, which it is, and that the data load okay and everything compiles okay. Then I'll load the inits and generate new inits, and we're all ready to go. Then I'll do my knee-jerk burn-in of 1,000 draws, hardly necessary in this model. And then I will monitor mu and sigma. Let's get some more draws quickly. This is going to go real fast. So we'll get 100,000 draws in about 2 seconds. And now the way you get the output, the Markov chain Monte Carlo data set output out, is you choose a particular node in the graph, and you hit the coda button. And coda is a block of R code that helps you check MCMC diagnostics, but we're going to use these numbers for a different purpose. You always get two files from the coda, hitting the coda button. One tells you what the object is and what the index is that it runs over. So this is the object mu, and it runs from iterations 1 to 100,000 after the burn-in. I always delete that file. And now this other file is what I want. It's the column in the MCMC dataset that corresponds to mu, and so I do a save as on it, and I put it somewhere. And to do that, be careful. It wants to save everything in that internal format of its format, star.odc. So you have to pick plain text, and now you can store it anywhere you like. Then you can kill that particular window off and go to Sigma, hit Coda again, kill that one off, and do the same thing. Store those in a particular directory of interest to you. And so now I did that with the model 1 here, which is the normal model, and then I also did it with the T model. And I can go ahead and get out of WinBugs and show you these files now. So I have a place called, as usual, go to short courses in eBay Google and NB10 log scores. So there's a file in here called nb10-model1-1-mu.txt, and it matches exactly what you would get if you clicked on that right here and stored those numbers in a file. Similarly for all the other ones. And so now I'm ready to run some R code in which I actually see how this goes. I'm going to need that R code, and there it is right there. So my first instruction to myself is to change directory in R to the place where those files are all stored. And you will want to download all those files and put them in a directory yourself, of course. So here, I know that place is called that, and so I start up an R. And I go and change directory to where that place is. NB10 log scores. Now let's go ahead and read all this stuff in. So first I read in the raw data values, and I sort them from smallest to largest for something I'm going to do later on. And then I read in everything else, and let's just go ahead and read all that stuff in and make sure it all comes in correctly. Having done the change directory, it should. And so it very quickly gets all those data sets. They all have the form. If you look back at them again on the web page, the first column is the iteration number, and the second column is the actual value in that particular draw in the MCMC data set. So I want to ignore the first column and pull out only the second column. And to do that, what I've done here is I've scanned that particular matrix in with 100,000 rows and 2 columns, put it in a matrix, and chosen only the second column. So now we have a single vector of numbers in each of those places called mu.g, and the G is for Gaussian and the T is for the T distribution. All right, and so you remember the story behind this says I have to actually evaluate the height of the density at the particular point in question. So I have to have a formula for the sampling distribution for the normal and for the sampling distribution of the scaled T distribution I'm using. Of course, we have dnorm already as the sampling distribution for the normal, the density for it in R. And we also have, I can write my own code to have the density for the T distribution. So I think I've shown you this. I've shown you some details. No, I'll get to that later. Okay. So I define this function, and as usual, it turns out the T distribution involves gamma functions, and so it's safer to work with the logarithm of the density and then exponentiate at the end. So that's how I wrote that code. And now what I'm going to do is I'm going to calculate the mean of all those evaluations of the T density at each observation. So first I'm going to set J to 1, observation 1. And then I'm going to calculate the mean of all those observations across all those particular draws in the MCMC data set and put that in a place called ls.contributions, row 1, column 1. And then I do exactly the same thing for the Gaussian model, row 1, column 2. And so here we go. I'll bring in this code and do it. It takes a few seconds to run. You might ask, why can't I do this inside WinBugs? And I'll show you in a few minutes that In fact, you cannot do it inside WinBugs, but there is something you can do that creates an approximate full sample log score that you can do inside WinBugs. Okay, so there we are. We've got that now. And now we can begin looking at the result. So I will, first of all, show you these are the individual contributions to the overall log score. And I've sorted the data values from smallest to largest. And what we see here is that the stuff in the first column is the T model, and the stuff in the second column is the Gaussian model. And so that observation 375, which is a big old outlier, is extraordinarily unusual as far as the normal is concerned, because the logarithm of the height of the density there is a really, really big negative number. And so I make a comparison. The minus 8.5 is bigger than the minus 12.2, so I put a 1 right there. And then I go through and look at all the other places in the data set, every single observation, and you find that sometimes the Gaussian model wins, but most of the time the T model wins in all those different iterations. In fact, it turns out that 71% of the observations are better fit by the T model than by the Gaussian model, just by adding up taking the mean of the ones and zeros there. And so now here's the overall log score. I go ahead and just take the mean of those log score contributions. And so the log score for the T model is about minus 3.08, and the log score for the Gaussian model is about minus 3.26, which is a smaller number. And so we would prefer the T model. And you don't have much experience, probably maybe none of you have any experience with the log score scale, but I can tell you that actually that difference is a big difference on the log score scale. So actually, the T model is a lot better than the Gaussian model on the basis of the log score criterion. And I can show you a picture that demonstrates where in the data set the T is better than the Gaussian and vice versa. And so that would be this picture right here. And so what it shows is that the points that have circles as their plotting symbol are from the T. Each one is an individual log score contribution, and the points that are from the Gaussian model have triangles. And so you can see the T model does a lot better in the left tail and a lot better in the right tail, and it also does substantially better in the middle of the data set than the Gaussian does. And there's a few places in the shoulders where the Gaussian does better, but overall 71% of the points are better fit by the T, and that shows up in an aggregate sense by having this log score be substantially higher than that one there. This matches something I've done in another file when we're going to get later on to Bayesian model specification section 2. Let's see if I can use the page down button. I've got some of this material in there for you, and I've shown you, I think, yes, here, if you look in here, basically I'm just doing exactly what I have just shown you now. So, starting on page 24 and continuing through page 29 of section 2 of part 5 of the organized notes, you will see exactly the same stuff I just did a minute ago if you wanted to have another go at it. So here I'm going to go ahead and peel that off because it gets to where I can't see anything else. All right, good. So that's how to compute log scores exactly, and it's how to compare two models with each other. That's interesting. Did I actually make any changes? All right, fine. No, it's all right. Never mind. Okay. So that's how to work with log scores exactly. But is there a way to get an approximate log score without having to do this slightly awkward thing of going outside of WinBugs and doing some post-processing in R? Yes, please. Yes. I will try to address that later today when I show you the algorithm that my student Milovan and I developed for answering the question, could the data have arisen from a particular model? My basic idea with regard to log scores is I'm going to continue to look for a model that has a bigger log score than the one I have now, even if it's only a little bit bigger. And I'm going to collect in my ensemble of models all the ones that, in succeeding order, smallest log score, next one, next one, next one, next one, until I get to one that seems like I can stop. And then I can decide either to choose that model or I can do model averaging across the ones that are in the ensemble. That's basically my way forward. That's something I'm going to cover later. So if you can hold that for later, there's going to be quite a bit of material on that. I talked with David Spiegelhalter once. They didn't go the log score route. They went the DIC route, this thing that they invented called the deviance information criterion, which has some substantial drawbacks in relation to log score. And I asked him one time why they didn't do log scores, and eventually he said, I don't know. I've read your papers on this, and log score is clearly better. One of the things that makes it better is that log scores work with any Bayesian model that's capable of generating a predictive distribution. And that's every Bayesian model that there is, namely not only parametric models, but also non-parametric. Bayesian non-parametric models can be compared with log scores. DIC, which I'm about to show you in a little while, only works with parametric models. Would have been nice if there was, pardon, yes? No, you have to be able to sample from the predictive density from any given model, and that comes out as a standard consequence of any sort of fitting in the Bayesian story, parametric or non-parametric. So out of those DP package routines, for example, there's a way to access the predictive distribution for the next observation. You can take draws from that predictive and use them to compute the log scores. That's correct. The thing I said a second ago is that the deviance information criterion, which I shouldn't really be talking about yet because I haven't introduced it to you yet, it only works with parametric models, Bayesian parametric models, whereas the log score approach works with any model that is capable of generating a predictive distribution, namely all Bayesian models. So since we like, when possible, to stay within the realm of RJAGs or WinBugs, is there a way to get log score directly inside that package? The answer is no. Although the developers of WinBugs and RJAGs could easily have put it in there if they wanted to. And maybe I should talk to Martin Plummer about putting it into RJAGs. But there is an approximate way. There is a way to get an approximate version of full sample log scores, and it goes like this. We have seen from this expression here that the predictive we're interested in evaluating is the sampling distribution with respect to the posterior. So another way to write the full sample log score is like this. It's the average of the logarithms of the expectation of something. Wouldn't it be nice if, I'll just talk about this more generally, for some unknown quantity x you're interested in, the logarithm of the expectation of x would be approximately equal to the expectation of the logarithm of x. If that were true, then we could reverse the order of the log and the expectation here, and calculations would simplify, and we would be able to do this calculation inside WinBugs or RJAGs. Because then when we're done, the full sample log score would just have this simple expression where we average over the data and we average over the MCMC draws and just calculate the logarithm of the height of the predictive. Now, star, this thing right here, is a special case of asking the general question, when is it true for some function f that f of the expectation of an unknown thing is approximately equal to the expectation of f? In other words, when is it true that the calculating the f and calculating the expectation commute with each other? You're allowed to interchange them. And people have asked this question before because it comes up a lot. in particular, something quite definitive can be said if f has a special form. So let's think about the one we're interested in. The function f we're interested in here is the log function. What's it look like? Well, it goes down to infinity as x approaches 0, and it goes up to minus infinity, rather, as x goes to 0, and it goes up to plus infinity as x gets big. But it has a special way it does that. Namely, if you pick any point on the function and draw a tangent there, the tangent always lies either on or above the function. Anywhere on the log function, that's true. And if you pick 2 points on the log function and connect them with a straight line, that's called a secant. The secant always lies on or below the function. Functions that are like that have a special name. Clearly, such a function, one informal name for it is we could call it bowl-shaped down. And the fancy name for it is that function is concave. And the functions of that kind always have those 2 properties I just mentioned a minute ago. The tangent line to the function at a point always lies on or above the function. And the secant line connecting any 2 points on the function always lies on or below the function. So that's the story about things that are concave. There are, of course, functions that have the opposite behavior. Let's think about our old friend f of x equals x squared. It's bowl-shaped up, and it has exactly the opposite behavior. The tangent always lies on or below the function, and the secant always lies on or above the function. So maybe something special happens with this business about interchanging the function evaluation and the expectation with concave or convex functions. And the answer turns out to be yes, and we actually know this already. So something interesting happens with f of x equals x squared. We know for any uncertain x, an expression for the variance of x, you can calculate it by going expectation of x squared minus the square of the expectation. So now, take that and put it on the other side. And so what we've just seen is that with f of x equals x squared, you get that the expectation of x squared, which is the expectation of the function, is greater than or equal to the square of the expectation, which is the function of the expectation. So, and that's true for any uncertain thing. I could talk about it in terms of random variables if you're more comfortable with that. Any random variable x, we know the variance always has to be greater than or equal to 0. Therefore, this has to be true. And this turns out to work for any convex function. With such functions, you always get the expectation of f is bigger than or equal to f of the expectation. Let's call that property A. And using the same logic, you can find without much trouble that the opposite thing happens for concave functions. With such concave functions, the expectation of f is always less than or equal to f of the expectation. Let's call that item B. These 2 facts together, people call Jensen's inequality for the guy who first did it. And so here's a little summary of Jensen's inequality down here. If f is convex, then the expectation of f is greater than or equal to f of the expectation. If it's concave, it's the other way around. Now, that's great as far as it goes, but in other words, that tells us that if we try naively just to go ahead and switch the role of expectation, that says that we don't expect to have those 2 things be equal because the inequality says greater than or equal to in our case. So what's really missing from Jensen's inequality, and I really only noticed this for the first time just trying to prepare these notes for you guys when I was working on it yesterday, unfortunately, the inequality doesn't help to quantify how close to equality those two things are. And that's what we really want to know. It would be nice if Jensen's inequality gave us some sense of how far off things are. But at least we can try it now and just see in a numerical example how far they're different. So with the NB10 example, the 2 sampling distributions being compared are the normal on the one hand and the t on the other hand. And so model 1 consists of IID draws from the normal curve. And the parameter vector theta 1 is the mu and the standard deviation, the mean and the SD. And we have our old familiar formula that the sampling distribution under the normal looks like our old friend 1 over sigma squared to 2 pi e to the stuff, right? That's just our normal density. So the logarithm of that has a simple expression, minus log sigma, minus a half log 2 pi, which turns out to be about 0.9 when you calculate it, minus a half, minus 1 over 2 sigma squared times how far the yi is from mu squared. So far, so good. Model 2 was the t distribution. That has a much uglier sampling distribution. The density function for the t looks like this. gamma of some stuff over gamma of some other stuff, sigma times the square root of nu times pi, 1 plus some stuff squared to the power minus nu plus 1 over 2. So kind of ugly, but we can easily take the logarithm of it and use the log gamma function when we need to. And thank goodness the Winbugs people and the RJAGs people, of course in R we know there's the L gamma function, we've used it already, and the Winbugs people have something called log gam that does the same thing. And so here's the log of the density. For the T, it's got 1, 2, 3, 4, 5 terms in it, kind of ugly looking but easy to program. And so I wrote some Winbugs code to try out this approximation and see how well it works. Let's go back over here and look at that code. So now we want to go to the web page and catch this story here. This is now a new Winbugs model that will calculate the approximate log score inside Winbugs. Don't have to do it outside. So let me start a new notepad and put that here. Actually, no, I'm going to go into Winbugs and stick it in there. Let's do that. So let's look at the form of this and see what's happening here. The first part of the model is identical to what we had before. We put a prior on each of the mu and the sigma. And the likelihood loop is the same as before up through this part here. But now I'm going to create a new quantity called log predictive density for observation I. And it has in Winbugs language exactly that expression I just showed you a minute ago. So if you look at minus log sigma minus 0.9 stuff minus 1 over 2 sigma squared yi minus mu squared, and then look back in the Winbugs code, they're the same. So I'm simply evaluating that log density expression that I worked out by hand. And now these two lines here are the same as before. And at the end, to get the approximate full sample log score, I just take the mean of those log predictive densities. And now that will be a node in the graph, and I can ask, at the end, I can ask for its posterior mean, and that will be my approximate log score. So let's do it. So I do another new, and I go back to the web page and grab the data set again. Put the data in. And I go ahead and get those initial values again. I need that to be a little bigger. And go back and grab them as well. And now we're ready to run a new version of the model in which we're actually going to get the log score also. So here we are checking the model, which I will warrant to you works because I did it yesterday afternoon. Now let's bring in the initial values and finish initializing everything. And I'll do my ritual burn-in of 1,000. And this time, the principal thing I'm going to monitor is just the approximate full sample log score value. So let's go ahead and monitor that node. Now I can get my 100,000 updates, refreshing every 10,000. And it's going to take a little longer now because it's got to calculate these 100 numbers and average them, but it's not that much longer. And now I can go ahead and do the stats on that. And there it is. The approximate full sample log score computed entirely within Winbugs is minus 3.291. And I shall now remind us of the exact one. So returning now to the handwritten stuff, minus 3.291 is the approximate one for the Gaussian model, and the right answer is minus 3.262. So it's off by about 0.029 on the low side. When I do exactly the same thing for the T model, it's off by about minus 0.015, again on the low side. And when I compute the exact difference between the two and the approximate difference between the two, in fact, the T model has been exaggerated to look better than the Gaussian model by a little bit, by about 0.014 on the log score scale. And you'll notice that the absolute value of this particular quantity here is smaller than the absolute values of either of those two numbers going into that calculation. And so what's happening is that we have a biased method of approximating what we want, but we use it twice and compare them with each other, and some of the bias cancels. That's a nice thing about a biased way of doing something. Doing it once is not necessarily a good idea because you'll get a biased answer, but if you do the same bias thing on two separate things and compare them, some of the bias may cancel and you'll have a better, a more accurate sense of what's going on. So we would have drawn the same conclusion here with the approximate method, that the T model is a lot better than the Gaussian model. It slightly exaggerates on the log score scale how much better it is, but it arrives at a similar conclusion. So I only just sat down yesterday afternoon to try to figure out how to do this in WinBugs, and this leaves open a new little research project for one of my master's students, namely, let's now start comparing the exact and approximate full sample log score for their model discrimination abilities, see if they're about the same or if one of them is a bit better. I'm expecting the exact will be a bit better, but I don't know how much, so we'll have to see. In fact, in getting ready for today and figuring out how this works in WinBugs, I actually did a little bit of original research because I may at least, I don't think anyone else knows this yet. There's a, sorry, thank you. Let's go back over here. There's a little section in this document called What LSFS is Not. I think I can find that. I can probably see if I can Control F on it. Let's try is not, see if we can find that. Yes, what LSFS is not. Isn't Control F nice? So I may have mentioned to you before, I'm forgetting whether I have, but a guy called Murray Aitken about 20 years ago published a paper as a red paper before the World Statistical Society, so a big deal paper called Posterior Bayes Factors, in which he basically said, well, I've told you last time that the problem with Bayes factors is that you have to calculate the expectation of the sampling distribution with respect to the prior, and that's a problem because the prior will often be diffuse, and so that's a highly unstable quantity. So Murray Aitken just said in an ad hoc fashion, I don't like the way that looks. I'm going to work out the expectation of the sampling distribution with respect to the posterior distribution. I'm going to call it posterior Bayes factor, and I'll write a paper before the Royal Statistical Society about how it works. And he, in fact, showed that it actually did a pretty good job of discriminating between models in a whole bunch of examples. He was thoroughly reviled by everybody in the discussion. The only people who commented pretty much were Bayesians, and they all said, the rules of probability only work in one way. You can't just make up new rules of probability just because you like something better than the ones that the things that the rules of probability tell you to do. However, I made a little calculation back when I didn't understand what I learned yesterday. I made a little calculation for people who might think that full sample log scores were the same as Murray Aitken's posterior Bayes factors, which were heavily reviled. I made a little calculation in which I showed how they were different. And all I did in this calculation, I never noticed it before, is I just showed that posterior Bayes factors are an approximation to full sample log scores, and they are exactly what you get by the approximation of interchanging the role of the logarithm and the expectation. So what Murray should have done, and is publish a paper back in 1991 in which he said he shouldn't have called them posterior Bayes factors. He should have called them approximate full sample log scores. At that time, full sample log scores didn't exist, but if he had seen what was going on, he could have published a paper called Approximate Full Sample Log Scores and shown how well it did on comparing one model with another, and his paper would have been applauded instead of being reviled. And so that's the new little insight I got by trying to get ready for today. In fact, what Murray did was okay. It's just that he came up with a story for selling it that was not okay. He made it look really bad to Bayesians, when in fact it's actually a perfectly respectable approximation to a good thing to do. I don't know yet how good the approximation is. That's, as I said, something that one of my master's students and I need to figure out. But at least Murray, as far as I'm concerned, is off the hook, and I will stop reviling him from now on, which is something that I did just along with all the other Bayesians for several decades now. So let's take our first break. VC Ops, I'm going to stop now for 10 minutes, and we'll start right again at 10:15. So let's begin again, please. I feel uplifted by how many people have shown up in the end today. We are now almost back up to 50, some sort of number like we had at the beginning of the course. That's really marvelous. Thank you all for coming. So I would like to take you through some of the material in section 2 of the Bayesian model specification. In particular, we'll get right to understanding what this DIC thing is, and I'll show you how to use it and what some of its drawbacks are. So there's some stuff at the beginning of this part that I'm not going to brief now. Oh, thank you. There's stuff at the beginning of this part here that I'm not going to brief because we've talked about it before, about De Finetti's exchangeability representation theorems and so on, and how Bayesian nonparametrics comes naturally out of De Finetti. Then I talk about how people often cheat in building their models, and so then I talk about the calibration cross-validation idea is in this particular document called three-way cross-validation, 3CV, which is the name that Milovan and I used to have for it, but I think CCV is better because it emphasizes that the point of it is calibration. Then I talked a little bit about that example I showed you last time with my student Fuskakis about creating a utility function for variable selection in logistic regression models. Then I talk about log score and motivated a little bit more in here. We've already seen how that goes. Let's take a moment to see how you might go about approximating the log score in a simple model, and it will lead us directly to a motivation for this thing called DIC. So I'm now on page 12 of part 5, section 2. So we have our simplest possible model in which the yi is given, at least the simplest possible model for continuous data, in which the yi is given mu or IID normal mu sigma squared with sigma known, and then we put a conjugate normal prior on mu with the parameters mu 0 and sigma squared mu. Let's take a highly diffused prior on mu. That would correspond to having sigma squared mu be really big. And the result will be that the posterior for mu is approximately simply a normal distribution centered at the sample mean y bar and with a posterior variance given by sigma squared over n. And then the predictive distribution, equation 11 on this page, for the next observation is approximately simply a normal distribution that's related to that one. It's still centered at y bar, but of course it has a much bigger variability because we're trying to predict the next observation, not just learn about the parameter. And so there's a sigma squared over n term from not knowing the mu, but there's also a sigma squared term from not knowing what the future will bring. And so when you bring them together on the variance scale, you get sigma squared times 1 plus 1 over n. And the cross-validation log score, ignoring linear scaling constants, looks like this. This is called model 0, so LSCV of model 0 given the data vector y. You simply add up, or I could have averaged, but adding up is good enough, the sum of the logarithms of the heights of the predictive for observation j given the data vector with observation j set aside. But by the same reasoning, the predictive for observation j with observation j set aside is a normal distribution centered at the mean with observation j omitted, and the predictive variance is now not sigma squared times 1 plus 1 over n, but 1 plus 1 over n minus 1. And so now we get the expression at the top of page, the next page, I guess that would be page 13 in equation 14. And the logarithm of that predictive, the height of the predictive, turns out to go like some constant C1 minus some constant C2 times the sum of squared deviations between the jth observation and the mean that you get by omitting observation j. Now, if you've ever studied the jackknife, you may know this already. It's an interesting fact that's related to the behavior of the jackknife, and you can prove this by induction, that the sum of squares that appears on the right-hand side of equation 14 is just equal to some positive constant times the usual sum of squares, in which I don't omit any observations at all. That's a kind of cool thing you can show. So finally, the result is that for a positive number C2, the cross-validation log score behaves like C1 minus C2 times the sum of squared deviations between each observation and the mean. So in this model, the log score is almost perfectly negatively correlated with the sample variance. In other words, if the sample variance is big, the log score is going to be small, and that will be a way of saying that the model doesn't fit very well because we would have been surprised by observations that came from that. But people in the generalized linear models world have a concept that they like called the deviance, which is simply minus twice the log likelihood. And you remember we had that idea also inside BIC, where we took minus twice the maximum log likelihood value. But here the deviance, which is a function of mu, you simply calculate minus twice the log likelihood at the point mu. And when you write that out in the Gaussian model, you get an expression that's identical to expression 17, except the C0 and the C1 don't matter, and the C3 is again a positive number. And so check it out. The cross-validation log score in this simple model is strongly related to the deviance idea, because we get the same sum of squares. Here, here it's the sum of squares yj minus mu squared, deviance evaluated at the data generating value mu, and then for log scores, it's sum of squares yj minus y bar squared. So if I were to evaluate the deviance at the sample mean, it would have a direct relationship to log scores in the following direction. When log scores are big, this deviance number is small, because look how C2 and C3 are both positive numbers, but the log score expression has a minus in front of C2, and the deviance expression has a plus in front of C3. So big values of log score correspond to small values of deviance and the other way around. So that introduces the deviance information criterion. This idea is about 10 years old now. Given any particular parametric model, P of y given theta, Spiegelhalter and his colleagues defined the deviance information criterion, which they abbreviated DIC. They were trying to motivate it by analogy with other information criteria. And you'll remember how BIC works. It's the sum of two terms, one of which measures the model fit or lack of fit, and the other one which measures model complexity or number of parameters in the model. And so by analogy with the other deviance, the other information criteria like BIC, also like AIC, the one that Mr. Akaike invented, which is similar to BIC except it has a different penalty for complexity, they do the following. They compute the estimate d of theta bar of the model lack of fit as measured by the deviance. And notice how that's exactly the same thing we would get if we took d of mu here and put in theta bar, now becomes just y bar, our best guess for the parameter theta, which is mu in this model. And then all of a sudden, log scores are perfectly related to deviance in the negative direction. Okay, so they start with an estimate d of theta bar of model lack of fit as measured by deviance plus a penalty for complexity equal to twice the effective number of parameters of the model. So they call that number PD, the effective number of parameters PD. And so they define DIC in equation 18 there on page 13, namely, d of theta bar plus 2 times the estimate p hat of d. Theta bar is the posterior mean of theta, and their idea is naturally enough that models with low DIC values are to be preferred over those with higher values, and that matches what we saw about log scores. Models with high log score are better than one with small, low, and so therefore low, and since they're negatively related to each other, low DIC means good. Now this works perfectly if you can simply read the number of parameters in the model directly from the model. For example, in our little Gaussian model, PD is 1, and you don't even have to estimate it because you can see there's only one parameter in that model. When it's difficult to read directly from the model, and that can happen in hierarchical models because you can't tell how many parameters there are in hierarchical models. And what I mean by that is the following. Remember, with the in-home geriatric assessment data, we had a model that looked like this. Yi given, let's see, Yi given lambda I were independently Poisson lambda I. Is that readable in the back of the room, or should I enlarge? Can you get it? And then we had that the log of the lambda i's were related linearly to a predictor term, which was a 1 if you were a control, rather 1 if you were treatment, and 0 if you were control. But then we had a plus EI to describe the extra Poisson variability, and the EIs were IID normal 0 sigma squared. So if you were counting parameters, how many parameters does that model look like it has? Just simply finding things that look like parameters and adding 1 every time you find one, you'd get what? I guess 3, right? Because there's a gamma 0 and a gamma 1 and a sigma squared. But really, because these random effects are in here, the effective dimensionality of the model in terms of kind of something like parametric complexity is substantially higher than 3, because if you were trying to fit this model, it's taking a position that's intermediate between the position in which everybody has their own unique lambda and the one in which all the people in the treatment group have the same lambda and all the people in the control group have the same lambda. And in fact, how big sigma squared is picks out a point on that continuum between those extremes. And the effective number of parameters in this model will typically be substantially larger than 3. It'll be somewhere between 2 on the one hand and the total sample size on the other hand, which I think in this experiment was something like 570 something. And so the effective number of parameters is some number in that range between 2 and 570. And you can't use BIC on models like this because BIC does not correctly count the dimensionality of the model. And you can't use AIC for a model like this because AIC also doesn't correctly count the dimensionality of a model. The reason that Spiegelhalter and his colleagues invented DIC is that they wanted it to be an improvement upon AIC because they figured out a different way to estimate the effective number of parameters in the model than simply counting how many parameters there were. So like it says here, when PD is difficult to read directly from the model, for instance in complex hierarchical models with random effects, they motivate the following estimate, which is easy to compute from standard MCMC output. The estimated effective number of parameters of the model is the difference between two things that look the same but are not. The posterior mean of the deviance, that's d of theta bar, minus d of theta bar. And I should have said it the other way around. Bar applied to d of theta minus d applied to theta bar. And those are two different quantities. The first term is the posterior mean of the deviance. And the second one is the deviance evaluated at the posterior mean of the parameters. And WinBugs will estimate these quantities for you, and so will RJAGs. And so now we can go back and put that PD hat into equation 18. We can combine equation 18 and 19 and get an expression for DIC in which all the components are calculable from standard MCMC output. Why this should be so, why equation 19 should be so, is a mystery that would take us too long to unravel here. So I'm just going to leave it as a mystery, and you can read their paper to see why that works. No, it's not. And in fact, I'm about to show you an example in which we can see with our own eyes that the actual number of parameters is 2, and yet WinBugs gets the effective number of parameters with this DIC criterion as negative 66. And so your question is right on point. There is no guarantee that this expression will be positive. So there's a level of ad hocery to the DIC story that is still present even after 10 years. When they published the paper, they took them a long time to publish. people they'd put the button for DIC inside WinBugs several years before they published the paper explaining how it worked and why it was supposed to be a good thing to do. And people kept bugging them to publish the paper. And finally, when they did publish the paper, it was also honored to be a red paper before the RSS, and there was all this discussion. And of course, all these smart people started looking at it and said, wait a minute, that might not work under the following conditions, and under the following other conditions, and under the following other conditions. And so by the end of the discussion, Spiegelhalter and his colleagues were essentially in the position of saying, well, this is a partially baked idea here, and we are not prepared to withdraw the DIC button from WinBugs. It's still in there. And it will still cheerfully produce negative values for estimated numbers of parameters in the model under some conditions. But I will show you how to improve on such negative estimates as we go along as well. In this model, we can just count how many parameters there are. And so in theta bar is just y bar. So look, in this little simple model here, minus DIC is going to be practically perfectly positively linearly correlated with the cross-validation log score. And the same would be true with the full sample log score. So in this simple model here, choosing your model by maximizing LSCV or LSFS, the full sample version, and by minimizing DIC would be approximately equivalent behaviors. But full sample log score has the advantage that it never does that nasty thing about estimating the number of parameters and having the estimate go negative. And also it has the advantage that it works for Bayesian non-parametric models as well as parametric ones. So we have, Milvan and I did some research in which we looked at the relationship between DIC and cross-validation log scores. We created a little world, I'm now on page 15, in which we were comparing two models. One was a fixed effects Poisson model. Let's talk about a one sample problem where model 1 is just that the data are IID Poisson, and model 2 says no. The model is rather like the in-home geriatric assessment model, except there's no predictor variable in there. It's just a log lambda equals beta 0 plus the normal error term. So that's a log normal mixture of Poissons. And now model 1 is a special case of model 2 when sigma squared in equation 24 is identically equal to 0. So we can now compare and see how well these two different methods, log score and cross-validation, do at discriminating between those two models. And on page 15, we did a simulation study in which we varied the sample size and the value of beta 0 and the value of sigma squared. And we tried out all four possible combinations in which the data generating mechanism was either model 1 or model 2, and the assumed model was either model 1 or model 2. And then we compared to see which one did better. And you'll notice that in the case of when the assumed model is a fixed effects Poisson, the two things are almost perfectly negatively correlated, and there's a mathematical reason for that. But when the assumed model is the random effects Poisson, they are less strongly negatively correlated, and there's a reason for that as well. When you start seeing pictures like the ones on page 17, you start saying to yourself, well, now these are not identical model comparison criteria, so that opens the possibility that one of them is better than the other one. The most egregious place in which DIC fails spectacularly is in mixture models, where you're trying to, for instance, compare a model that is a Gaussian with only one Gaussian with a model that's a mixture of two Gaussians, for instance. DIC fails spectacularly for such models. This was pointed out by another very sharp statistician named Sylvia Richardson in the discussion. And the WinBugs people responded to that not by withdrawing the DIC button from WinBugs altogether, but by writing special code into WinBugs that detects whether you're fitting a mixture model or not. And whenever you're fitting a mixture model, it only then temporarily disables the DIC button. So essentially, out of the discussion came one big class of models where it completely fails, and they did the responsible thing there. they dummied it out of their code when they wrote some model detection code that found out that the user was specifying a mixture model, and then dummied it out, not available anymore. But there are still situations in which DIC misbehaves, and I guess we'll look at one of those now. No, actually, first I want to show you is how they go comparing log scores and DIC in the in-home geriatric assessment example. So here are 4 different possible models for that data that we looked at before. You could pretend, as we did in Model 0 some weeks ago, that the data were like draws from 2 independent sample Gaussian distributions, which is sort of a silly model. You could try a 1-sample Poisson model that pretends that the treatment and control lambdas are equal. That's like saying in-home geriatric assessment has no effect. You could try the 2 independent samples Poisson distribute with each control and treatment have Poisson with their different lambdas. And we saw weeks ago, that was equivalent to the fixed effects Poisson regression model. And then finally, the random effects Poisson regression model that I showed you some weeks ago. And so I'll show you in a minute how to get DIC inside WinBugs. Here's a little screenshot on how to do it. And here are the results at the top of page 20. The average of the deviance is the thing called deviance bar is in the left-hand column. Then the deviance evaluated at the posterior mean is the second column over. Then the effective estimated dimension of the model is p hat d. Then DIC, and then log score. So let's study this for a while and see if DIC seems to be behaving correctly here. How many parameters would there be in model 1, which compares 2 independent sample Gaussians? Pardon? 4, right? A mean and a variance for each one. What does DIC get? It says 3.99, so it's worked just fine there. And that's kind of interesting. That expression that we saw before that looks so counterintuitive, bar d of theta minus d of theta bar, turns out to exactly track the right number of parameters in that model there. Now going back to model 2. Oops, I went back too far. Going back to model 2, suppose we pretended that the data were Poisson and the treatment control had exactly the same effect on things. How many parameters would there be in that model? Just 1. And check it out. DIC gets 1.02. So again, it's right. Third model has each group is Poisson, but they're allowed their own separate lambdas. So that model has 2 degrees of freedom in it, two parameters. And DIC gets it right there as well, 1.98. And now, very interestingly, you start getting numbers that BIC and AIC could never have coped with. In the random effects Poisson regression model, the effective number of parameters is about 143. And so I mentioned to you that that number had to be somewhere between 2 at one extreme, when sigma squared, the between person variability as far as the random effect goes, was 0, and the total sample size 500 and something or other. So what was that number? I think I've got the data set up here. 572. So somewhere between 2 parameters at the one extreme and 572 at the other extreme. And WinBugs decides that the effective amount of variation in there is that there's about 144 parameters being estimated. You would never have been able to work that number out by any other means. And so when it works, this is a pretty interesting piece of technology. Now we're supposed to trade these things off against each other, and the DIC column does that. Just looking in the DIC column, is Model 2 better than Model 1? DIC for Model 1 is 1,700. No, lower is better for DIC. So clearly 1,500 is better than 1,753, and I'll tell you that that's actually an enormous difference in DIC because it has because of the minus twice log likelihood story, it has a chi-square sort of flavor in terms of comparing the two things, and that's just a huge difference on a chi-square scale. What about log score? Does it say that Model 2 is better than Model 1? Remember, big values of log score are better, and minus 1.3 is bigger than minus 1.6. And now you begin to get a sense of what's going on the log score scale. 1753 versus 1501, that's an enormous difference on a chi-square sort of scale, and it only translates into a difference on the log score scale of about 0.24. So you can see what I mean before. Small differences in log score actually can correspond to pretty big differences between the models. Does it think that Model 3 is better than Model 2? Yes, again. And in fact, it was able to achieve a decrease in DIC of about, of about 4 on 1 degree of freedom. And again, if you make a chi-square sort of calculation, that is statistically significant. And interestingly, minus 1.314 is therefore roughly statistically significantly different from minus 1.316. That makes me worry about that approximation I showed you earlier, where the approximation error was on the order of about 0.015. And then finally, the REPR model, does it look better than all the previous models? Substantially better again. We get numbers that are on the order of 1418. Here I got 3 numbers in the REPR row because I decided to run it over again with different monitoring runs with different random number seeds to give you an idea of how big the Monte Carlo noise here is. And so the 141 part is pretty solid. The 8 part is sort of solid, could be an 8 or a 9. So you can see there's some Monte Carlo noise in these numbers. But 1418 is a lot smaller than 1497, and minus 1.18 is a lot smaller than minus 1.31 on the log score scale. And so here's a little naive sort of scatterplot that shows all 4 of those models plotted against each other, and the correlation between the log score and DIC is about minus 0.98. So these 2 methods on these 4 models are tracking each other very nicely. But DIC can misbehave. And so now I want to show you a data set in which it does. I invented a little data set here that was generated from the negative binomial distribution. You remember how the negative binomial works? You count how long it takes until you get a specified number of heads in tossing of coins. Rather than asking how many heads you get in a specified number of tosses, you do it the other way around. And so the success probability in the simulated data was 0.82, and the number that I was supposed to wait for was around 11. Or at least the R that has something to do with how long you have to wait was 11, and I forget the exact relationship here. And the data set comes out with integers ranging from 0 to 6, and it has a mean of about 2.4 and a variance to mean ratio of about 1.22, so there's fairly substantial extra Poisson variability here. Now, certainly we could use standard diffuse priors and try it and see what happens, so let's go ahead and try it. So if you go back to the course website, down here I've got a story that says, example in which DIC badly misbehaves. So here's the model file, which I will grab. And I'm going to have to kill this off because it gets too big for its britches on the screen. So let's bring the model in. And since P is a probability, I gave it a uniform distribution. Beta 1, 1, you'll remember, is the uniform. And since R is a number that lives on the positive part of the real line, I gave it one of those gamma epsilon epsilon priors. This is one of those knee-jerky sort of priors for positive quantities. These are not very good prior choices, but there's nothing to prevent me inside WinBugs from using them. Okay, now I want the data file. And there are 17 observations, and I showed you what they were a minute ago. So let's bring them in also. Stick them in a file as well. And one more new file for the initial values. And so I'm going to start things off exactly at, oh, that's interesting. In fact, WinBugs has a very literal interpretation of the negative binomial in which R is forced to be an integer. And so it allows me to put a gamma prior, a gamma epsilon epsilon prior on R, but the actual values that R is going to sample have to be integers in its way of looking at the negative binomial, because it really is having to do with how many coin tosses you have to do until you get a specified number of successes and so on. All right, so now we can run this guy and see what happens, and I'll show you now for the first time how to actually get a DIC value. So we read in the model and check it, and it's fine, and we load the data, and it's fine, and we read in the initial values and generate some other ones, and everybody's happy. And we do the obeisance to the knee-jerk update. Now we'll go ahead and monitor P and R and y.new, the predictive. And now the new thing is under the inference menu, there's a little button we've never talked about before called DIC. You click on it, and it creates this little thing called the DIC tool. And having done our burn-in, we can now begin monitoring for the purpose of calculating the DIC. So I hit the set button, and now I go and get 100,000 updates, refreshing every 10,000, and this should go pretty quickly. 100,000 updates in 1 or 2 seconds. And now let's look at the posteriors before we look at the DIC value. So the posterior for P, we started out being a uniform, you remember, on 0 to 1. And we haven't actually learned that much about P from the data because quite a lot of the posterior is still the same as the prior. See how there's that flat place in there? It's basically just said that the posterior is the same as the prior from 1 down to about 0.75, and then values less than that are pretty unlikely, increasingly unlikely. So some learning has taken place, but also the prior has had a pretty strong influence. And that's because 17 is not a very big sample size in the negative binomial story. And the stats for P go like that. You might say that 0.73 is not very close to that data generating value I had of 0.82. But look, the posterior SD is huge, and you aren't going to get much from one data set anyway, right? So, all right, what about R? With this particular prior, R just goes crazy. If you look at the history of it, it's usually quite small, but every now and then it's getting values like 2,000, 3,000, 4,000, just really absurd values, actually. So this is not a very smart prior for R. And its stats are correspondingly weird, with a mean of about 22 and a standard deviation of about 85. We just don't really know much about what R is, that particular very diffuse prior. What about the predictive, though? Here's the predictive density. I'm not sure if you can visualize what the histogram looks like, but check it out. There'll be a bar at 0, and the bar at 1 will be taller than that, and the one at 2 will be taller than the bar at 0 and about the same height as the bar at 1. And then it'll fall off with the 3s and the 4s and the 5 and the 6 and so on. It kind of looks like this model fits the data pretty well, and in fact it does from the predictive. And yet, in fact, this time we get an even worse answer than I put in the notes. It says that the estimated number of parameters in this model is negative 80, and that therefore the DIC value is negative 15.5, which is a utterly rubbish idea. DIC is not supposed to be able to go negative, and especially PD is not supposed to be able to go negative, and yet without any trouble it went negative. So what?
Is that a function of not having enough data?
It is not. It turns out that in order to get DIC to work reliably, you have to do the following thing. For the PD hat part of DIC to work, you have to find a parameterization such that all the marginal posterior distributions of all the parameters are approximately Gaussian. And having done that, you will then force WinBugs to evaluate the deviance on that parameterization rather than on the one that you might have started with, and that will turn out to fix this problem. In other words, when they invented DIC, they had in mind a situation, and actually the answer to your question, I guess that's one way to answer your question. If we had a huge amount of data, then with practically any scale on which we chose to parameterize things, we know by the Bayesian central limit theorem that the marginal posteriors would all be close to normal. So with an enormous data set, this can't happen. But with a small data set and a choice of parameterization where things don't look very close to normal, you're in trouble. And so, unfortunately, the current state of the art with DIC is that the WinBugs doesn't try to find such a parameterization for you. It just gives you bad results when you didn't start with such a parameterization, and then the onus is upon you to try to find a reparameterization in which things actually do work okay. That's the current state of the art with DIC. I can go partway toward doing that here, and this might not be such a good example for what I have in mind. I'll show you a better example with the T density on the NB10 data, I guess, after lunch, or in a while anyway. But we can already do better. The problem here is that it doesn't really want to, well, let me say it this way. WinBugs has a kind of strange relationship in this model to the parameter R. Thank you. The official definition of the negative binomial in terms of that business about counting how many tosses until you get a specified number of heads would force R to be an integer. And yet it perfectly, and in fact, if I had tried to start things off with a number other than an integer, it would have given me an error. And yet it's perfectly willing over here in the prior to allow me to put down a continuous prior on R, not an integer valued prior. That's kind of strange. Because if I was allowed to mess with the prior on R to make the resulting parameterization look more normal, I showed you what that posterior looked like. It had an enormously long right-hand tail, and so since it's a positive thing that has a hairy long right-hand tail, what's the natural parameterization to use? Instead of working with R, you work with log R. And similarly for P, to make it look more normal, what's the standard transformation with something that lives between 0 and 1 to try to make it look more normal so that it doesn't mess around with the boundaries, for example? What is the basis of logistic regression? What do we do there? Log of the odds ratio, right? And so we could certainly do that. I could create something called L. L, and that's going to be the log of the odds ratio. And I'll give it a normal prior centered at 0 with a small guy like that. Oh, you don't like L? Because it looks like a 1? Looks too much like, okay, so what if I call it ELL? Are you happy then?
That's great.
Okay, good. So I don't blame you. It's a reasonable objection. Now down here at the bottom, I have to tell it what P is in terms of ELL. So if you recall, the inverse transformation is, one way to write it is 1 over 1 plus e to the minus L. So that's the simplest way. So that should work. And now instead of putting in P equals 0.82, I'll open up a little R session and work out what the logit of 0.82 is. So log of 0.82 over 0.18 is about 1.5. So let's start things off at L equals 1.5. So let's try that and see if we get a more plausible DIC value. So okay, I'll check that model. The new model will replace the old one, and it doesn't like something. Did I type that wrong? Is that how you do that in WinBugs? 1 capital E minus 6? Maybe I'm supposed to go 1.0 E minus 6? I'm supposed to say that? Let's find out. Oh, it's fine with that now. Thank you very much. I believe we're all set now. Now let's monitor both P and L and R and y.new. And now we'll get DIC now. Let's ask it for 100,000. That's right. It's what it's doing is it's creating what I've been calling in this course the MCMC data set with one row for each MCMC iteration, one column for each thing it's monitoring. Until you press the DIC set button, it does not create the bar D of theta column and the D of theta bar column. It doesn't create those, so it won't be able to. All right, so now let's see what's the posterior for L look like. It started out as normal with an enormous variance, and it ends up looking sort of normal, but with a much smaller variance. That's kind of cool. Quite a lot of learning just happened for L. It used to have a mean of 0 and a standard deviation of 1,000. Now it has a mean of about 2.7 and a standard deviation of about 2. So a lot of learning has occurred for L. And the implied density for P now actually is kind of interesting. It is concentrated largely on quite large values. So very different answer than what we had before. And it shows you, by the way, this thing we've been talking about on and off for the whole course. Different ways of trying to be diffuse with small sample sizes can have dramatic effects on the posterior. What about R? It still looks obstreperous. Perhaps even more so. What about y.new? It still fits the data pretty well. Not quite as well, interestingly, not quite as well as before. And now let's get the DIC value and see if we've improved. Oh, it's even worse. Look, now it thinks the PD is 100 minus 169. All right, so over lunch I'm going to try to fiddle with this and see if I can find a parameterization that'll work better. But basically, DIC does not always work well. When it does work badly, sometimes you can rescue it by reparameterizing, but here I tried to do something constructive and it got even worse. I think it's because the worst thing to worry about was not the P, but the R. And if I try to work with log R, it's just going to say that's an inappropriate prior because it's supposed to be an integer, blah, blah. And yet it was quite happy to write down a gamma epsilon epsilon prior. So I don't really understand what WinBugs is doing in this example. And yes, you can. I could give R a Poisson prior, for example, with a really big variance. So, in fact, we could try that. You want to try that? Should work. Suppose we gave it both a mean and a variance of 100. That's actually that's quite informative, isn't it? Because that's like saying that the mean is 100 and the standard deviation is only 10, and so that's too big. So it's actually not that easy to do. You're right, but in principle you can. I'm going to go ahead and just get rid of this whole thing and try to do better for you after lunch. So beware of DIC. it can sometimes produce really weird answers. And yes, please. That's right. Unfortunately, yes. Anytime you know what the right number of parameters is because you can count them, and it's not producing a number quite close to the number you can count, you know it's misbehaving. So in the earlier example with the in-home geriatric assessment, all three of the first three models had very nice answers. When it was supposed to be 4, it got 3.99. When it was supposed to be 2, it got 1.98. So you have an immediate check when you can actually count how many parameters there are. We have to trust it in hierarchical models that it's doing something sensible. Yes. The reason I'm telling you it is that if I don't tell you what its defects are, it's a very readily available button inside both WinBugs and RJAGs, and you might be tempted to use it all the time for model comparison. And in fact, it does work sometimes as quite a good model comparison tool. It's just that sometimes it's really awful in that it doesn't know how to compute the effective dimensionality of the parameter space. So that's why I've gone on and on about this, trying to sort that out for us. So, then I showed you already the full sample log score calculations. I'm on page 24 of section 2 of part 5 of the organized notes. I showed you how to do those calculations. There's some stuff in here about large sample properties that I'm going to skip over because it's not that interesting for us now. So basically, I'm now on top of page 30 of part 2. And what it says here is, well, we now have 3 behavioral rules. Maximize the cross-validation log score, maximize the full sample log score, minimize DIC. And now you have an implementation question as a user with, let's say, 2 models to choose between. How accurately do these different rules discriminate between model 1 and model 2? And so I'll show you results from a simulation that Milvan and I did. Again, model 1 was just everybody is Poisson with the same lambda, and model 2 says no, everybody has their own lambda according to that log normal mixture of Poissons. So we built a new simulation study, and we worked out as a function of various values of the parameters, what percent of the time it got the right answer. Each different method got the right answer. This is an example for cross-validation log score with 32 observations. The right model was always M2, because here we simulated only values of sigma squared that were bigger than 0. So the right model is always M2. So when I say percent correct decision, I'm answering the question, how often does it get model 2 right when model 2 was the actual data generating mechanism? And you can see as sigma squared gets bigger, it gets the correct decision more and more often, which makes sense. As beta 0 gets bigger, it gets the correct decision more often, which actually makes sense also if you stop and think about it a little while. And then there's some measures that show you how much farther LSCV is for model 2 away from model 1, and that difference, of course, gets much bigger as the sigma squared gets bigger and the beta 1 gets bigger. So even with only 32 observations, it gets the right model choice more than 90% of the time when the between person heterogeneity variance parameter is bigger than 1/2 for beta 0 equals 1, and when it's bigger than 1 for beta 0 equals 0. So it does a pretty good job even with pretty small sample sizes. And here's some pictures that show how they compare. They're in effect, they act like Bayesian decision theoretic power curves. The horizontal scale, I believe, is sigma squared, and the vertical scale is the percent correct choice of the right model. And the sample sizes range from 32 to 100. And column, I think what it should say is that row 1 is beta 0 equals 0, and row 2 is beta 0 equals 1. And actually, and then the dotted lines are the full sample log score, the long dotted lines. The red little dotted lines are cross-validation log score, and the solid lines are DIC, if I remember correctly. Did I give a No, other way around. DIC is the red, LSFS is the long dotted lines, and LSCV is the solid. So you can see everywhere you look in this table that full sample log score does better at model discrimination than either of the other two methods. There's never any situation in which it does worse. So pretty cool. Full sample log score. Then I have a section on why not Bayes factors, and I've already shown you that Bayes factors can really misbehave, so let's go over that. Let's jump right over that. Now we come to a section that relates to a question I had earlier. So now I'm on the top of page 39 of part 5, section 2. We now have a reliable way of, actually we have two reliable ways of answering the question, is Model 1 better than Model 2? Namely BIC on the one hand and full sample log scores on the other hand. Those are the two that I'm prepared to recommend to your attention. What about that other question? Is Model 1 good enough that it's okay for me to stop looking further for an even better model? Having compared amongst a bunch of models with full sample log score, we can certainly decide that Model 2 is better than Model 1, or the other way around. Let's say we decide that Model 1 is better than Model 2. That in and of itself, of course, doesn't say that Model 1 is adequate. It just says that Model 1 is better than Model 2. And so now the second question comes about, having found a Model 1 that's better than Model 2, is Model 1 good enough to stop? And as I said earlier, the real answer to that question involves decision theory and has to be answered in a problem-specific way, one problem at a time. But we can actually answer a question that's related to it in a fairly general way, namely, could the data have arisen from Model 1? If the answer is yes, then you might feel comfortable that it's okay to stop looking. If the answer is no, then most people would not feel comfortable in stopping there because we definitively have shown that the data could not have come from Model 1. So even though Model 1 is the best model you've looked at so far, the data can't have come from Model 1, so you're not done searching yet, pretty clearly, right? So all right, so how do we do this? And a natural approach to answering this question is to simulate from that model many times and develop a distribution of full sample log score values and then see how unusual your actual log score is in that simulated distribution. That would be a good way to do this. So this is related to an idea that has been in the literature for more than 15 years now. There's a paper by Gelman, Meng, and Stern that refers to a technique called posterior predictive p-values. And this method is still widely used around the world, even today, even though I'm about to show you that it's actually very badly calibrated. It can be very badly calibrated. And I've published on this before. Jamie Robbins published on it in the year 2000. Susie Bayari and Jim Berger published on it in the year 2000. And these guys are still not willing to back down and claim there's anything wrong with their method. Hal Stern is a reasonable guy. Hal just basically says, I don't want to talk about it anymore. Xiaoli Meng is a reasonable guy, and he pretty well says the same thing. He doesn't want to talk about it anymore. But Gelman still tries to defend this approach, even though you can show him over and over again that it's very badly calibrated. So what Milvan and I did was we have developed a method for accurately calibrating the log score scale and improving upon posterior predictive p-values. And so a flavor of what I'm getting at here, a simple flavor of what I'm getting at here is I can show you from something that happened in my course I just was teaching at UCSC. So let's go there. Actually, I'm going to have to download something else. So let me just take a second and go there. Maybe I'll do that during the break. I wanted to show you a simple example of this, but we'll just go ahead and jump right into the complicated example because there's a break coming up pretty soon. Um, so let me say again what the basic idea is. You have a particular log score value for this particular model. And you're wondering, is that a big log score or a small log score? And so an idea would be, like I said here in this paragraph, why not simulate from the model many times and get a log score each time and locate your log score in that distribution? If it's way out in the tail, then probably the answer to the question, could the data have arisen from this model, is no. And one way you can measure how far it is in the tail is with the only time in all of the Bayesian paradigm it seems unavoidable to calculate a p-value. Namely, you could work out the area to the right of that place if you're way in the right tail, or the area to the left of that place if you're way in the left tail. This is the only point in the whole Bayesian story in which it seems inevitable, and you can't run away from it to compute a p-value. And that's because this is an inherently frequentist way we're trying to answer this question. Could the data have come from this model? And we're answering it in the frequentist method. We're saying, let's go ahead and generate many log score values from this model and find out how unusual this one is. So we're essentially using Fisher's logic, except in this context here, that he never would have dreamed of. Yes, please. That's right. Actually, with log score, it's the other way around. Bigger scores indicate better fit. Actually, I'm wrong. Then we should only be looking in the left tail. You're right. Yeah, no, you're right. I said that too glibly. I was thinking about the example I'm going to show you after the break. I asked my students to, with the in-home geriatric assessment data, I asked them to, in each of the control and treatment data sets, we work out the variance to mean ratios. You might remember one of them was about 1.6, the other one was about 1.3. And I asked them the question, if the data really were from a Poisson, how often would you get a VTMR like 1.6? And that's exactly the sort of question here. What you want to do is to simulate from a lot of Poissons with the same lambda you have in your data set, calculate the VTMR each time, build a little distribution of VTMRs and see how funny this one is. And theoretically, that could have landed either in the right tail or the left tail, although it would typically only land in the right tail. And I'll show you that example after the break. So you're right. No, you're right, Tony. Really, we're only looking for discrepancies in the left tail. But here's the deal. Here's how the method that Gelman et al. Have developed. Here's how it actually works in practice. If they give you a posterior predictive p-value of, let's say, 0.04, then you know that there's something wrong. Because the actual well-calibrated version of their p-value would be smaller than that and might even be a lot smaller. It might be 0.004. But if they give you a posterior predictive p-value of 0.4, which naively indicates that the model could just be fine, a well-calibrated version of their 0.4 might itself be more like 0.04, 10 times smaller. And in fact, the correct decision is that no, this data set could not really have come very plausibly from this model. So like it says here on this page, their method is actually conservative in the sense that it does not announce a problem as often as it should. In fact, sharply does not. And so Milovan and I have a method for fixing that, which I think I'll tell you about after the break. So we're at time for our break. Let's stop now and return in 15 minutes. So VC Ops, we're going to stop now and start again at 11:30.